In this video, we will look at testing a center of a distribution that is not from a normally distributed variable. So if you recall, the number tested variable, so the number of samples tested per hospital for MRSA, was not normally distributed. And you can look at the distribution here. First of all, you can look at it and see that it's very skewed. It is not centered about a single unimodal distribution. And we can go ahead and look at the Quantile Boxplot. We can go ahead and look at the normal Quantile plot. And if you look at the Quantile Boxplot, actually you can see the very long tails. You can also see the very long tails in the regular box plot. And in the normal Quantile plot, you can see this very dramatic curve. In fact, if we make this larger for you, you can really see that the bottom sides of the confidence bounds aren't even visible, nor is the lower part of the line. And remember, for normality, what we're really looking at here is these black dots to follow the line and be within the confidence bounds. And we simply don't have that here. If we look at the subset of the 30 that was drawn for the notes of the number tested, and we do a distribution for that, we can again see a very skewed distribution. I can take a look at the normal Quantile plot. And again, we see an almost identical pattern here in the normal Quantile plot of this sample of 30. We are a little bit more visible in the confidence bounds, but again, it cuts across both confidence bounds and then arches quite far up. And we have one very large outlier here that will really ultimately influence the distribution. This is not a normal sample. Even though our sample size is 30, we can see it is not normally distributed, and we know that the underlying population is not normally distributed. So it would be very hard to adhere or cling to the assumption of normality here. My sample size is just on the border of that rule of thumb, and I know that it's not a normally distributed sample. So I don't want to test my mean here. What I want to look at is a test of the center of my distribution value. And so in this case, we can take a look at doing what is called a Wilcoxon rank sum test. We have our observed means here. And what we want to do is compare them using a non-parametric test. You could also compare the medians. We're going to compare the means for the non-parametric test. And you do this in the same way that you do testing means. Under the red drop-down, test mean. It brings up this test mean box again. We're going to specify our hypothesized mean here of 242.75706. That is our hypothesized mean. That's our hypothesized mean from our full distribution of 177. We can ignore the Z and T test option here because we certainly don't know the standard deviation and it doesn't follow a normal, so we can't do a Z. Remember, Z and normal are synonymous, and we're not assuming normality. What we want is the non-parametric Wilcoxon signed rank test. So check that box and press OK. Now JUMP will give you your t-test statistic as well as your Wilcoxon signed rank statistic. We can ignore the t-test options right here. We can just go ahead and say that this doesn't hold because we are not assuming normality. What we want to focus on is the signed rank results. We can ignore the minus 103.50. The signed rank value will change depending upon your sample size. Remember, what the signed rank test does is it essentially puts all of these values in order, and it will look at whether or not is above or below this value. If it's above, it gets a positive. If it's below, it gets a negative. Those are summed up and compared to a distribution. So it doesn't actually matter what this value is. You will never see the signed rank value reported. What you will see is our p-values here. And so we have a p-value here of 0.0307. 0.0307. We're doing a two-sided test here. It's equal to, not equal to. So our null hypothesis is that the center of these distributions is the same. Our alternative hypothesis is that the center of these distributions is not the same or not equal to. Again, we know these are the alternative hypotheses because they do not contain an equal sign. They only contain greater than or less than signs. And by the way, greater than the absolute value is the equivalent of a not equal to sign. That's what we want. Now it says the t-test here, but that's simply because it's aligned with this. This is still our correct p-value. This is still our correct p-value here. So we're going to go with this. The reason that you see the blue, so much blue here on the t-test is our t-test would actually fail to reject. Look at our p-value on the t-test. It's very, very large. The reason for that is we have a giant standard deviation. But remember, we're not doing a t-test. We're doing a non-parametric Wilcoxon signed rank test. We're doing this test because we have not normal data. Even with our sample size of 30, we are not willing to assume normality because this is clearly not normal, and our underlying distribution is clearly not normal. So we are going to use the signed rank test, and that will be our p-value. And it's okay that our t-test said it wasn't different and our signed rank says it was different, and we can feel comfortable with the signed rank because we've reviewed our assumptions. The assumptions for the t-test are not met, so it doesn't actually matter what these say. We're only concerned with what this says because we have evaluated our assumptions and determined that the signed rank test is more appropriate. We will then conclude that we are rejecting our null hypothesis of equality and concluding not equal. So we can give the p-value of 0.0307 because it's less than alpha as our evidence that we have concluded that the centers of these distributions are statistically significantly different by the Wilcoxon signed rank test. It's very important that you say that, otherwise people will assume it's a t. So you say it's a Wilcoxon signed rank test and then give the p-value and put it back in words to say that our sample has a statistically significantly different value than our underlying or true population. Very straightforward to test one mean versus a hypothesized value. You can do it with a z-test if you know the sigma or the variance. That's rare. It will almost always be a t-test where you are using your estimated standard deviation, or if you have assessed for normality and you've decided not to assume normality, it will be the Wilcoxon signed rank test. In all cases, follow the 10 steps, and in all cases, report your substantive conclusion back in the words of the question itself so that it is clear to your reader what you